This will be a video on converting between polar and rectangular coordinates. Let's first label a point in the plane as x comma y, and we'll call this angle here theta. The distance from the origin to the point we'll call r. And what we see first off is that there is an implied right triangle here that has a base of x and a height of y. Let's go ahead and calculate the value for cosine of theta for that right triangle. Cosine of theta would be the adjacent side over the hypotenuse, so that will be x divided by r. And if we solve that for x, we get x is equal to r cosine of theta. This gives us x in terms of r and theta. Similarly, let's find sine of theta. That will be opposite over hypotenuse, so that will be y divided by r. And similarly, let's solve for y. We can then write y is equal to r sine of theta. Another obvious relationship that we see is x squared plus y squared is equal to r squared. These are the three primary equations that take us back and forth between the two coordinate systems. There's one other equation, and that is based on the tangent of theta. Tangent of theta is going to equal y divided by x. And that one is used sometimes, but not quite as much as the other three, but still, of course, super important. So those are the four equations that take us back and forth. Let's take a look at a couple of examples. Let's suppose we have the vertical line x equals 4. Well, if we want to convert that over to polar, we're going to take that x and replace it with r cosine of theta. We now have an equation with r's and thetas, so that's a polar equation. Ideally, we solve for r. Just like in Cartesian, we often will solve for y. In polar, we often will solve for r. So we need to divide both sides by cosine of theta. And if we rewrite that by converting cosine to secant, we would have 4 secant of theta. And you can probably see the pattern here. If this was x equals 5, we would end up with 5 secant of theta. If x was equal to negative 10, this would be negative 10 secant of theta. So this is how we are going to write vertical lines in polar coordinates. Let's come back over to the next example. X squared plus y squared equals 16. We have a relationship right here between Cartesian and polar, seeing that x squared plus y squared is r squared. So we'll just replace the left-hand side with r squared. We'll take the square root of both sides, and then we'll recall that r is representing a positive number, or a non-negative number more precisely. It's measuring the distance from the origin out to our point, so it should be a non-negative number. And this is how we are going to represent a circle in polar coordinates. More precisely, a circle centered at the origin. So r equals 7 would be a circle of radius 7 centered at the origin. Let's try going the other direction. Let's suppose we have a polar equation, and we would like to convert it to a rectangular equation. We don't have an equation for simply r. We have an r squared. We don't have an equation that has just a sine of theta. We have an r sine of theta. So the trick here is going to be to multiply both sides by r. If we multiply both sides by r, we can then do a pretty easy substitution. On the left side, we have x squared plus y squared. And on the right side, we have 6 times y. So that's our Cartesian equation. Looks like it's probably a circle. To figure out exactly what the characteristics of this circle would be, we'll complete the square. So right now we have that. We complete the square in y. We take the coefficient of y, divide it by 2 and square it. That gives 9. We have to add 9 to the right-hand side also. That allows us to factor the left side into y minus 3 quantity squared. And on the right we have 9. So this tells us that we have a circle that has a center equal to 0, 3, and we have a radius of 3. There's lots of equations that we could move back and forth with. These are 3 of them. This will get you started.